Alright, hey, welcome back. So, time to talk about clocks and interrupts. And this is where microcomputers, mini computers, start to be more than just another computer that's challenging to program. Being able to work with interrupts at the hardware level is a lot of fun. It's also challenging in terms of debugging and so on. So let's dig into this with a relatively straightforward interrupt-based system. So I'm going to go to the peripheral handbook, and I want to look at the clock in here. So if I just search for clock, I see there's this thing KW11-L. It's called the line clock. This is a clock that's driven off of the power line. So if you're in the States, 60 hertz power line, this clock ticks 60 times per second. And it's called a KW11. And if I just search W, I can get that to the section. So the line clock's going to be on page 332. And so here we go. Line time clock KW11 divides time into intervals of either a 60th or a 50th of a second. And it's got a single control register, 7546, with 2 bits. One bit is an interrupt enable, and the other bit is used to indicate when the clock has ticked over. All we have to do is basically turn on this interrupt bit, and it will begin throwing interrupt requests 60 times a second, more or less. Now this is simulated, so it's not going to be incredibly accurate. So the register address is 7546. The interrupt vector address is 100. So when a interrupt occurs, there's a particular location in memory where the CPU will look for the address of an interrupt handling routine. So for this interrupt from the line clock, it will look at location 100. And it expects to find 2 things there. The word at location 100 is an address for an interrupt handling routine. The next word is a 16-bit value which says what should the new processor status word be. So remember, the processor status word indicates the result of condition code 0, negative, and so on. It also includes what the current priority level is of the CPU. This clock interrupts with a priority level of 6. That's a pretty high level. 7 is the highest. So in our interrupt vector, we're going to set the priority level of the processor to 6, which means if other things at the same priority try to interrupt, they'll be denied until the priority level of the system goes below 6. Priority level 7 would be things like power fail, super urgent conditions. So let's put together some code and make this less abstract. So I'm going to go into my work area, and I'm just going to make some clock code. And so this is KW11-L. So we'll do absolute addressing, and let me set up my start location. So we'll do some of the usual stuff that we do. We'll set up a safe stack area around 40,000 octals so we don't bump into our code, for example. And then let's enable interrupts. So if I look at this register, I want to basically turn on bit 6. If it's equal to 1, that's an interrupt. If it's 0, it's non-interrupt mode. So let me set up some symbols here in the beginning. I'll do LKS equals 177546. So that's the clock status register. And then we'll have some output LEDs for displaying information. What we're going to do is make this thing count. Every second it will bump up a counter by 1, and we'll just let it go with that. So let's go ahead and enable interrupts. So I'm going to move and I want to put a 1 here, and I'm just going to do 0 zeros here. So I'm going to do octal 100. So immediate 100, comma LKS. And that says interrupt enable equals 1. And then we're just going to spin here. So this is just an infinite loop, branches to itself. Without interrupts in the system, this would do nothing. But we're going to set up an interrupt handler. So put some interrupt code here. So we'll go down to location 100. That's the clock's interrupt vector, and we'll put in the address of our interrupt handler. We have to define what handler is. And then I'm going to set the processor status word to 300. So looking at our programming card, processor status word is these 3 bits right here. So for level 6 we want a 1, a 1, and a 0. So bits 7 and 6 should be 1s, and then the rest should be 0. That should be the correct IPL. Sets priority level to 6, so that we need higher level priority interrupts to actually interrupt our interrupt handler. So we'll do an end, and we'll put the label start on there, just say we're going to start at that location. We also need to define our interrupt handler. So there's our handler label, and whatever address this gets stored at in memory, that's what will get loaded at location 100. We can look at that in the simulator in a bit. So what should we do when we get an interrupt? Well, we only have one thing that can interrupt us, that's the clock. So we're just going to go ahead and bump up a counter. So increment a counter. Actually, let's decrement a counter. So we'll count down from 60 to 0. Branch if it's equal to 0, then we'll go to time up. So we'll do things here. Otherwise, we'll say return from interrupt. So we keep waiting. Time up. So 60 ticks have occurred. Let's just increment R0 and then move R0 to our LEDs and then return from our interrupt. So we'll show the next number. Alright, we need to do a little bit of wrapping up here. So let's make our counter. That'll be a word. And in the beginning of our code here, let's move. So we want 60 decimals, so we can do caret D 60, comma word, counter. So we count down from 60. At time up, we'll increment R0, move it to the LEDs, and then we need to reset our counter. And then return from the interrupt. So let's also clear out R0. So each second we should bump this up and display it, and that should pretty much do it. So set up our stack pointer, set our counter to 60, clear our display counter, enable interrupts, hang out here forever. When an interrupt occurs, it will look at location 100, see the address of handler, jump down here, count down from 60. If we get down to 0, it will come down to time up, otherwise it'll just return. At a time up, it'll bump up the value we're displaying, display it, reset the counter to 60. That should be everything we need. So before start, let's start somewhere reasonable. So we'll go ahead, reassemble that. We'll reload this. Now if I look at my program counter, it's 1000. We're good to go. If I look at my interrupt vector, it's 1024. If I look at the code at location 1024, it's where we decrement our counter and either come down here to increment R0 or return and so on. So I feel like this should be good to go. Let's go ahead and continue it, and let's flip our display to show the display register, and there we go. It's counting once per second, started at 0 and just counting up. So that's interrupt driven code, and Control E here. If I make one change here, if I just move a 0 into that clock register and reassemble that and then reload that and continue, nothing happens, right? Our register is not counting. It's never displaying the value of R0 out there. It's just got the last value that we had. If I were to deposit 100 into this register and then continue, we're back to counting, right? Because that's turning on that interrupt bit right here. So this is how most code actually works. It's interrupt driven. A lot of our code is mostly sitting in something like this. On the old VMS system, this was called the null process. It was just a branch to itself, and everything else happened in response to events, software or hardware interrupts. So most of our devices have interrupt options. For example, when we do console input, we can poll a status bit to see if there's a character available, but we can also set up the console hardware to say when a character arrives, generate an interrupt. And if you look in this peripheral handbook down in Appendix A, you can see the interrupt vectors for all the different types of events that can occur. Some of them are software events, like a breakpoint trap or an illegal instruction. Some of them are hardware events, like when the keyboard has a character available, it can jump to location 60. When the console is ready to receive another character to display, it will jump to location 64, and so on. So lots of interrupt-based processing going on. All right, that's all I've got for now. I'm not sure what the next unit will be, but this gets us off and running into some of the more micro mini computer specific topics. All right, thanks.